Alrighty, Calculus AB rock stars. I mentioned in one of the last few videos that this topic 5, antiderivatives and integration, is really split into three pieces, where the first two pieces are kind of teasers, and then the third piece really ties everything together. Well, good news for you, you finished your first third of this topic, where the first third was all about the indefinite integral. And the indefinite integral, general idea, was take the antiderivative and don't forget that plus c, right? So if we were given a function f of x, then the indefinite integral gives this, which really means, I don't know, we could say something like the antiderivative of f of x is capital F of x plus c. Right? Maybe we could call this like the general family of functions that's the antiderivative due to that plus c, but either way, it's an equation. And so far, all we've said is that this is just a way to go backwards from what we did last semester. But don't forget that derivatives weren't just meaningless. It wasn't just here's some rules to take a derivative. Derivatives actually told us something about a graph. So what do antiderivatives tell us? And at this point, we're actually going to forget everything that we've known about antiderivatives and integrals. We're going to move away from that for the next week and a half or so. And then again, once we get to our third part, we'll tie everything back together. So here we go. Given a function lowercase f of x on a closed interval from a to b, then a definite integral is given by this, which at first glance looks extremely similar to an indefinite integral, except they have these weird a's and b's up here. What does that mean? Well, we're not sure yet. And so we're going to define that and then see how we're going to work with that. And again, we are going to forget this antiderivative idea for the next few days. So for today and the next couple classes, we are going to temporarily forget the integral symbol means take the antiderivative, and instead we're going to focus on the idea of definite integrals. These integrals have values at the bottom and top of the integral symbol. We just saw that up above there. A is known as the lower limit of integration and b as the upper limit of integration. No surprises so far, as a was on the bottom of the integral and b was on the top. Traditionally, a is usually a smaller number than b, but as we'll see over the next few days, it does not have to be. It's okay if it's switched around. It's just more convention. All right, an informal definition, and we're going to improve on the definition of a definite integral like 5 times, kind of the same way where we started off with dx and said, oh, it's just notation. Then we said, well, no, wait, it kind of comes out when you do the differential. And then we said, no, wait, it actually means this. Well, we're going to bring the differential back in too, but same thing for our definite integral. Easy definition to start, not very mathematical, but enough to get you started. A definite integral gives the total signed area bounded by the graph of f and the x-axis along the interval from a to b. Notice then, if we're going to be measuring area, then the definite integral is going to give us a value as an answer, not an equation. Right? So normally what we're used to over the last few classes is when you do the integral of something, then your answer is an equation. But now when we bring the definite in, it's going to mean something somewhat unrelated for now, and it's going to say find the area from a to b and tell us that value. Now, I did also mention the idea of signed area. Signed area is the idea that above the x-axis, the area is a positive quantity, while below the x-axis, the area is a negative quantity. And we are going to build on that a little bit more over the next few days, too, about why should area ever be negative? What does that actually mean? We will get there. So for now, let's just take it on fact, and we'll try a couple examples, because the overall idea of signed area is very easy. So here we have a graph that is continuous on the closed interval from a to d, right? Never have to pick up my pencil until I get over to d. And we're going to look at the integrals, or the area, or the signed area, on different subintervals. So first, we want the definite integral from a to b of f of x dx. And from a to b, I think we can see over here, ABC, that from a to b, the area between the graph and the x-axis is 12. And because we're above the x-axis, it is a positive 12. Well, what if I wanted the area from a to c? That gets more interesting. From a to c, it starts again at a. Okay, so we know it's definitely going to be 12, but then we drop below the x-axis and we go to c. And if we're below the x-axis, that is a negative area, and so our total combined area, 12 minus 10, will be 2. What about from a to d? Well, from a to d, same idea. We already know that this is 12 minus 10, which is 2, and then we have to add 8 more. So 12 minus 10 plus 8. 12 and 8 is 20. 20 minus 10 is 10. You could have just done 2 plus 8, of course, as well. Great. That's the idea of signed area. Pretty easy, right? Now, we just looked at this where f of x was a general idea. It was, there is a curve over there, there's a graph. Look, we gave you the graph. How exciting. And we're going to stay fairly vague for the first half of today's lesson. Either it's going to be, we're going to give you the areas, we're going to give you the graph. And then the second half of today is going to go back to more of what we're used to, and we're going to say, okay, now you have an equation, and we're going to find the definite integral of that equation. But hold off on equations for now, and let's look at a few integration properties. Now, of course, many of these properties will not surprise you, but there will probably be one at least, maybe two, that will be a little bit new. So the first one is a property we already did. So essentially we're saying if we wanted the definite integral from a to c, but there's a point b somewhere in the middle, then it's okay to find the area from a to b first, also find the area from b to c, and then add those together. And I mentioned we had already done this. Of course we did. We did this up here. If instead of finding the area from a to c, which is, this is how we did it, you could find the area from a to b of f of x dx, because b is somewhere on the way to get to c, and then you could find the area from b to c, and notice I now dropped b down to the bottom because b is smaller than c, but it was larger than a, of f of x dx, and we saw that it was 12 and then a negative 10, which is where we got 2 from. So the idea that instead of thinking of this as one whole area, we can think of it as 2 small areas, 1 and then 2, is a fairly not scary concept. The second one, though, is a little bit strange. We like to measure our area from left to right. And generally, that is why our lower limit of integration is smaller than the upper limit of integration. We go from a to b. Now, you are allowed to switch these. So if you're not going from left to right, or for some reason you want to go the other direction, it's totally okay to switch the limits of integration. But it turns out that if you switch the limits of integration, you need to change the sign of your area. And maybe that's best illustrated with this 10 over here. So if I wanted the integral from b to c, moving left to right, of f of x dx, then we can see that that is negative 10. However, if you wanted to find the integral from c to b of f of x dx, right, and that would be moving this way from left to right, then it is equal to the negative value of the integral from b to c, which we found earlier. So it's the negative value of negative 10, which in fact makes this positive 10. So moving from left to right, this area is negative. Moving from right to left, the area becomes positive. And we are going to learn why that is later on. And for now, maybe you can think of it in terms of, well, no, we'll cover that later on. No reason to get too in-depth. This is already going to be a long video anyways. Okay, property 3. Just like with derivatives and indefinite integrals, you are allowed to split your function. So that means if they want the integral of two functions being added together, you can absolutely split it into the first function plus or minus the second function. Now, to me, that's actually kind of wild. It's much more interesting here than I think it is with other functions, because, for example, if they wanted you to calculate the integral underneath the equation x cubed plus x squared dx, you might say, I don't even know what the graph of x cubed plus x squared looks like. How can I find the area? But this allows us to say, well, okay, that makes sense. Why don't you just graph the equation x cubed, because you know what that looks like, I hope, and then also graph the equation x squared, and if you find the area under this one and the area under this one and add them together, it's the same as the area of their combined function, of that super function over there. All right, moving on through. Just like with derivatives and indefinite integrals, if you have a constant multiplying by your function, you are welcome to move the constant out to make the area easier. Again, if you had something like they said from a to b of 3x squared, and you're like, ugh, I don't want to graph 3x squared to find the area, well, move the 3 out, and now just find the area underneath x squared and multiply the final answer by 3. Last but not least, at first glance, this one seems a little bit weird, but I think as you think about it, it will not be as terrible. This one says if you integrate, if you find the definite integral from a to a, then the area between the curve and the x-axis is 0. All right, well, again, visually, always nice for those visual learners here. If I wanted to find my antiderivative from a to a of f of x dx, well, here's a, and then I move to a, well, that's just a point, right? And a point certainly has no area. So maybe that was a poor example. Let's call this point 2. If I wanted to find the area from 2 to 2 of f of x dx, well, this is the area underneath the graph, this line right here. But to find the area of a line, maybe think of it as an area of a rectangle, but just a really, really small rectangle. It certainly has a height, right? Area is, of course, base times height. This certainly has a height, whatever this is to get up here. However, its width, a line is one-dimensional. Its width is 0. So you'd be doing some height times 0, which means it has an area of 0. So easy enough to prove and probably not too scary to think about. Okay, I have a couple examples for you here, in particular example 2 and example 3, and I bet you guys could actually do okay with example 2 and example 3 without me, so I'm going to ask you to try it so I can take a quick pause and you guys can see how you're doing so far. So essentially what's happening here though is you are being given the area underneath some unknown graph f of x, and they're saying if you find the area underneath f of x, so between f of x and the x-axis from -2 to 1, the area is 9, and from 1 to 5, the area is -2, and they said now that we've told you some areas, find a different area, and you'll find that example 3 is very similar. So take a couple minutes, try each of them first, and then you can check back in and see how you did. All right, hopefully example 2 didn't give you too much trouble. I think example 3 is a little bit trickier, but you do not need to draw a graph for this. In fact, a graph might make things a little bit trickier. However, I'm still going to try, and we'll see how I do. So here's -2, here's 1, and here's 5 over here, right? So they're saying the area below the graph of f of x from -2 to 1 is 9. Well, if the area is positive, then I'm going to take a leap of faith and say that this is my positive area 9. Now realize it doesn't have to be. It could also be a huge area over here and a small one here. So this could be like 12 and 3, because 12 minus 3 is also 9. So we don't know what it looks like. We just know when you add all the areas together, you get 9. Cool. And then we also know from 1 to 5, the area is -2. So I'm just going to be lazy here and just put a 2. Great. This graph would meet the requirements of what is given right here. It's not unique. There's an infinite number of possibilities, but just wanted to show you what's happening. And then their question is, cool, now that you know those areas, how do you find the big area from -2 to 5? Well, if you didn't have a graph, what you do is you try to break it down from what's over here. You say from -2 to 5, that's too far. Let's do what we know. Let's start from -2 and go over to 1 of f of x, and that's going to be some of the way from -2 to 5. But we're not quite there yet. We need to also add on the area from 1 to 5 of f of x dx. So we need to also add on this area over here. And when we do that, well, we know that our first area was positive 9, and our second area is negative 2, and we find that the grand total area is 7. I bet many of you just said, oh, we can add them together, and yes, that's fine. You did not need to show all the work I did, but it's nice to see a visual and kind of ground this in what we've seen before. All right, example 3. Given all this stuff, calculate this. Well, the first thing I'm going to notice is that we're going from negative 10 to 6, small to large. And if we're looking at this, this is not small to large. This is large to small. This one is good, though. So I am going to take a quick second, and I'll try to color code here, and I'm going to rewrite this guy as the integral from negative 10 to 6 of f of x dx. And we are allowed to just flip the endpoints, flip those limits of integration. But if we do, what happens? Oh, it makes our answer negative. It's changing the direction. So maybe think of positive in the direction it's traveling, and if you switch the limits, you're traveling in the other direction, so now your answer has been multiplied by a negative. Okay, next up. Well, they're giving us information about two different graphs. First, about the area below f of x, or in between f of x and the x-axis, and they're also giving us information about g of x. And this function down here is one super function. They're like, what's the area beneath the graph of 2f of x minus 10g of x? And I don't know what that graph is, but I think if we split it into smaller pieces, we might have a better idea. So let's take a peek. How do we split this into smaller pieces? Well, I'm going to do two things at once. First, I'm going to have the integral from negative 10 to 6 of f of x dx. And you might say, well, wait, where'd the 2 go? I'm going to factor that 2 out front. Then we are subtracting off the area of g of x dx with the 10 moved out front. These two are exactly equivalent. Hopefully you're comfortable seeing that. And the reason I did that is because now we know this value and we know the one next to it. So let's finish this off. This becomes 2 times something minus 10 times something. And the somethings are, of course, given here. From negative 10 to 6 is negative 23, and from negative 10 to 6 of g of x is negative 9. I am then looking at 90 minus 46, which to me looks like 44. Great. The total area on this supergraph over here is 44 from negative 10 to 6. Okay, next up. Well, there's actually an equation here. Okay. Well, this says we want to find the area beneath the graph of sine of x squared. Well, at first glance, you might say, well, sine of x squared, I don't even know what sine of x squared looks like. And that's okay. You don't have to. Because they're just asking you to find the area from negative 2 to negative 2 of this graph, which means we're not moving anywhere, which means the area is 0. That's property number 5 up above. Now, speaking of equations, how do definite integrals work if you're given an equation instead of a graph or instead of just generic information about a graph? Well, as the definite integral measures the signed area between the curve and the x-axis, then we're probably going to need to look at the graph and calculate the area between the curve and the x-axis. So let's take a peek. Example 5. They want to find the area beneath the graph of 2, and actually I'm going to ask you to rewrite this each time. So what is the graph? The graph is the equation y equals 2, and we're looking on the closed interval from 0 to 3. So each time we're going to write that just to kind of cement this idea into our minds that we are looking at the graph of y equals whatever from something to something. All right, well, let's look at that graph. Y equals 2 is just a horizontal line, and we're going from 0 to 3. So here's 0, 1, 2, 3, and 1, 2, 3. Cool. So we have this line that travels horizontally across, except we're only looking from 0 to 3. So what are they saying here? Well, they're asking what is the area between, and hopefully we are somewhat comfortable with calculating area. If not, we're going to get lots of practice. This area is, or this shape rather, is a rectangle, and to find the area of a rectangle, we just need to do the base. That looks like 3 times the height. That looks like 2, and I think that's going to give us 6. So our final answer, I'll write over off on the left, is the integral from 0 to 3 of 2 dx is 3 times 2, which is 6. Not bad at all. So there is definitely an emphasis on this class, and really this class alone. There's a few others, but of sketching graphs, and it's a nice reminder. So I tried to give you a good variety of functions here to sketch. So let's move on. Okay, examples 6 and 7. These ones are a little trickier, but I'm going to still have you pause me and give it a shot because they're nothing terrible. I will help you with the graphs right now, though. So the first graph is the graph of y equals x, right? 1x plus 0, if you will. And we're looking from -1 to 4. The second graph is a little bit more strange. So we're looking at the graph of y equals the square root of 9 minus x squared. You might not know what that looks like off the top of your head. But I'm pretty confident, though, that if there's a squared and a square root, there might be a different way to write this. In fact, if we squared both sides, the square would undo our square root, and then maybe even added x squared to the left side. We get this. And just as a friendly reminder, this is a circle centered at 0, 0 with a radius of the square root of that, a radius of 3. And if you didn't know that, that's okay. It is not a make it or break it concept for this class, but you should know the equations of circles and ellipses. So let's go ahead and not forget also that we're looking just from 0 to 3. So why don't you guys go ahead and get these two functions graphed and try to find the area, and once you've done that, we will come back together. Ready, set, go. Alrighty, we are back. So graphing wise, if you already know how to do this, please skim forward and just see if you got the answer right. We have our x-axis and our y-axis. We'll need a couple quadrants here, I think. We're going to 4, 1, 2, 3, 4, 1, 2, 3, 4, -1, -1. We'll put the 2's in there. Great. And we know y equals x means the x-coordinate and the y-coordinate of the coordinate pair are the same. 0, and then we also go from -1. So we're looking at something like this, but hopefully with a better line drawn. There we go. Now, the tricky part here is, what is the area we're looking for? Well, we want the area between the x-axis and the equation. And so here is the ending and starting points in the equation. I see two different areas. I see a nice large triangle over here, but then I also see a cute little triangle over here. And we need both areas. So the integral from -1 to 4 of x dx equals, and I'm going to erase this, so there's not enough room here, but I'm still going to write it first just so we can see. Really what we're going to do is we're going to find, let's do this in colors, we're going to find the area from -1 to 0 of x dx, and then we are going to add it to the area from 0 to 4 of x dx, right? We'll treat them as two completely separate areas. Something I do see people do here, which is not what we're looking to do, is they see this line and they go, oh, that's just one big triangle, let's find this area. But the area is always between the graph and the x-axis, and this area down below is not between the graph and the x-axis. So backtracking quickly, let's get this done. The area below the x-axis, how do we find the area of a triangle? Well, the triangle is just half of a rectangle, isn't it? So let's do the area of a rectangle, which is, of course, base times height, and then we'll take half of that. I know some of you like to write base times height over 2, and that's space saving, and that's totally fine. No complaints. Plus, and then we have the one in blue, so it's also 1/2 times the base times the height. You really don't need those parentheses. Okay, finishing this off, it looks like the base and the height are both 1. 1 times 1 is 1. Half of 1 is 1/2, so the area of the yellow triangle is 1/2, but it's below the x-axis, so we make it negative. Then we have our blue triangle. Our blue triangle is 1, 2, 3, 4 by 4, which is 16. Half of 16 is 8. And then we add these together. 8 minus 1/2 is 7, and 1/2, or 15 halves, or 7.5, whatever works for you. So as long as you can do two things, definite integrals aren't terrible. What are those two things? Well, the first is create the graph. That can be tricky, algebra-based. And then the second is, can you find the area between the graph and the x-axis? And that could be tricky because it's geometry-based. But putting algebra and geometry together, you should be successful with today. So let's look at a few more, and then we can do our last page, and we're done for the day. All right, how do we graph this? Well, technically, x squared plus y squared equals 9 is maybe better written as x minus 0 squared plus y minus 0 squared equals 3 squared. You can see the Pythagorean theorem relationship here. This is an HK form where our HK both have minuses, so we're doing the opposite of each. And then we have my radius of 3. So circle centered at 0, 0. And having a radius of 3, you're going to find very quickly how terrible you are at drawing circles on a coordinate plane. It just never looks nice, especially if you do your endpoints first. I've actually found if you just try to draw a circle first and then put endpoints on it, that's pretty good, that it works out much better than the endpoints first, and you'll see why right now. So radius of 3, centered at 0, 0. So I just went from the center and went out 3 in each direction, and here is my circle. Look how circular that weird thing is. Great. Now, we are only looking from 0 to 3. So 0 to 3 is, of course, this piece. And so I think that's actually going to get rid of half of our circle. There's only this part over here. But then if we had this half of the circle, look, we have a positive piece and a negative piece. They'd just be 0. And that would be a silly problem. But we need to remember that we aren't actually using the implicitly defined equation. We isolated y. And working backwards to isolate y to go from here to here, you had to introduce a square root. And to see all solutions of a square root, you need plus minus. The plus minus can be seen on this, where the plus is the piece where y is positive, and the minus is the piece where y is negative. However, in this original, there is no plus minus in front. They only have a positive, an invisible positive here, which means there is nothing below the x-axis either. So looking at this, what they mean is just a quarter of this circle. And that, I think, is the giveaway to our answer. If we want to find the area between the circle and the x-axis, we need to do the area formula for a circle, but then cut it into quarters. So as a reminder, area for a full circle is pi r squared. A quarter of that is just 1/4 pi r squared. Okay, pi, our radius I think is 3. We saw that earlier. And if we continue out then, it looks like we're getting 9 pi over 4. Ta-da! The last 4 questions on this page are supposed to be all on you guys. I will go over them just because we're on the video, but I would hope that you pause me, try all 4 of these, and just very quickly skim the answers to see what you did right, or if you did wrong, maybe stop skimming and listen in quickly. Once we're done with these, we are going to do 1 extra problem on the back, and that will conclude our lesson for today. So go ahead and take a few minutes, try each of them, at least get the graphs for each, and then we will chat. Ready, set, go. Alrighty, you're back. I'm going to get each of these graphed, and then after or as I'm graphing them, we can maybe talk about the equations too. Right? The absolute value of x, normally y equals x looks like this. When you do the absolute value, though, it still keeps the positive part, but then flips the negative part up. So this is called a linear absolute value equation. It makes a v-shaped graph. We are only looking for the area from 0 to 2, and so that is just a nice little triangle. So we'd say something like this. We'd say the area, or the integral, from 0 to 2 beneath the graph of x dx is, and then we do our formula for the area of a triangle. Base of 2, height of 2, 4, half of 4 is 2. Yay! Second one. We're going from negative 2 to 2 of negative 2x plus 1. This one is a little bit trickier in terms of x-intercepts and all those fun things, so here we go. I'm getting my graph. We're going from negative 2 to 2. If you want to find how far you need to go for your endpoints, you might even want to just make a really quick input-output table. We know the smallest x is negative 2, and the largest x is positive 2. So if I substitute those into my equation, I should be able to find the outputs. Negative 2 substituted in is 4. 4 plus 1 is 5. Positive 2 is negative 4 minus 1, which is negative 3. So I need to go from negative 2, comma 5, 2, 3, 4, 5, all the way over to positive 2 comma negative 3. And then we know, of course, that this is a linear function, so somehow these have to connect. The problem is I don't think it's going to go through the origin just based on this plus 1. We know the y-intercept is 1 over here, right? So I probably should have done a better job drawing this. That's awkward, but that's okay. We'll do it like this. We'll make it work for us. There we go. And then we're just going to erase these and say 1, 2, 3. Ha! Perfect. Okay, so we have this graph looking pretty nice, but then again, the issue, well, we'll see the issue right now, is when we go to turn this into triangles, we have this triangle right here, and look at that little piece over there. I'll shade that in right there. That's all one triangle. And then we have our second triangle, which is this guy, and again it has an itty-bitty little piece. And in fact, it turns out that this x-intercept is extremely important so that we can figure out the length of our base of each triangle. Well, we can find x-intercepts. How do we find x-intercepts? I think an x-intercept, this is going to be the point something comma 0. So I think we can just set 0 equal to our function. Negative 2x plus 1, add the 2x to both sides, divide, and we find that the x-intercept is 1/2. All right, now we're in business. Let's find our total signed area. Negative 2 to 2 of negative 2x plus 1 dx is going to be the area of the green triangle first. So it's going to be 1/2. The base, this is negative 2, and then we move a half further. So to me, that is negative 2.5, except not negative. It's positive base. There we go. And then the height is 5. Not bad. Cool. And then you could put a plus next, or we could skip to it. We know this yellow triangle is below the x-axis, so I'll put a minus. 1/2 the base. Well, you can see that this is 1.5, so our base is 1.5, and the height is 3. All right, don't go throwing extra negatives around there. Just for now, let's use a negative if we're below the x-axis, positive if we're above. Continuing to simplify, this becomes, let's do the 5 out front. So we get 5 halves and then 2.5. We do that around the world thing, right? 4 plus 1 is 5, so times another 5 halves. Minus, and then over here we have 3 halves, the 3 times here, and then the 1.5 is again 3 halves. Very exciting. So it looks like 25 quarters minus 9 quarters. 25 minus 9 is 16 quarters, or a very nice area of 4. 2 to go. This one to me is looking like another circle equation. So let's start by maybe rewriting this guy. We have y equals the square root of 1, the positive square root. That'll become important shortly. Square both sides. And then add our y minus 3 to the left side, or x minus 3 squared to the left side. I'll even write out the y minus 0 squared equals 1, which is 1 squared. What is this telling us? It's telling us that we have a circle. It will be an ellipse if there are coefficients out front. This is going to be a circle that is centered at opposite of h, opposite of k, and has a radius of 1. Let's draw said circle. Okay, now again, let's do the center first. 1, 2, 3. Could have done better with my axes. I will do better. Hopefully you didn't draw too much yet. Something like this. So we have 1, 2, 3. I went out to 4 this time because this is the center, but the radius dictates what my circle looks like. It's a radius of 1 in each direction, not just all 4 directions, but infinite number of directions, right? And then we connect them together to find that full circle. But I'm not going to try that because it's never going to look good. Instead, we're just going to freehand sketch a circle. But before we do that, let's look at what area interval we're asked to find. We're only looking from 3 to 4. So 3 to 4 is just that interval right there. So instead of doing one whole circle, we are just looking from here to here, right? Just half a circle. Except, same as before, the square root is positive, so we're only looking at this quarter circle where the y values are positive and we're on the interval from 3 to 4. Pretty nice. This is just another quarter of a circle here then. So if I wanted to find my area, it's going to be 1/4 pi times my radius squared, or pi over 4. Last but not least, we had to deal with the graph of sine, and you're probably looking at that going, ugh, sine, trig functions, this one had pi, there's probably some weird pi stuff going on. I think it's actually easier than that. So let's take a peek. So we need the graph of sine from 0 to 2 pi, and we should be somewhat familiar with the graph of sine, and we'll discuss a few of those important properties here. We're going from 0 to 2 pi. That's the length it takes sine to complete a full period. If you never remember where sine starts from, just start with a point, sine of 0. And sine of 0 is 0. We input 0, we output 0, which means we start at the point 0, 0. 2 pi is the period, so we end at 0, 0. Once you're here, you just need to sketch in the general form of sine, something better than that. Let's find my halfway point, right? Something like that. Cool. There we go. This is the reduced interval of the graph of sine. Of course, it goes forever, but we don't need that part. So then the question becomes, okay, well, how do we find this total area? We do not want to make a mistake and assume that because sine and cosine are associated with circles that this is a circle right here. It is actually not a circle. A circle, if you graph it, will look something like this instead. That was a pretty good circle. Go me. They are not the same graph. So you cannot say that this is pi r squared divided by 2, or half a circle. In fact, I don't know what that area is off the top of my head. There might be a mathematical way to calculate it, but for us today, we're not going to do that, because instead, what we do need to realize is that sine has symmetry, and whatever the size of this area, we're just going to say it's positive area, this area down below is the same, except below the x-axis, it's a negative area. And if we're tallying the total area from 0 to 2 pi, we add up some area, and then we take away the same area, which leaves us with a total area of 0. Alrighty, so there are example problems for today that you guys had to work with. We have one concluding note and one of the AP exam's favorite graphs that we saw a few times last semester, so I thought it was important to bring it back this semester. Vocabulary first. If a function is integrable, which just sounds like I'm chewing marbles every time I say it, then that function is able to be integrated. Now, to us, working with definite integrals, if a function is integrable, then that means we are able to find the area, the signed area, between the function and the x-axis. So what makes a function integrable? Well, luckily, this is the same as pretty much all of our theorems so far this year. And this isn't presented as a theorem, but it really kind of is one. It's nothing you'll need to regurgitate on the AP exam. But in order for a function to be integrable, f must be continuous on a to b, right? There shouldn't be any gaps. However, if f has a finite number, finite meaning you can count the number of removable discontinuities on a to b, then f is integrable. So this is a little bit different than differentiable. It's the same concept, but in order to be differentiable, you couldn't have any gaps. In fact, there were a lot of criteria for differentiable, right? Remember, differentiable had to be continuous and it had to be smooth. There couldn't be a sharp point, couldn't be a vertical tangent. This one does have to be continuous, but there can be sharp points. That's still continuous. And there can even be removable discontinuities. And you might remember that most commonly a removable discontinuity shows up as a hole, right? And so what that's saying then is one hole in a graph, or 10 holes, or even a million holes, if you can count all of them, doesn't affect the area. It's only if you were to have an infinite number of removable discontinuities or other types of discontinuities that we'll see in just a second that would make it so we cannot find the area. So last example. Given f of x equals this scary looking function right here, and then x equals 4 generates an output of -1, find the area beneath the graph from 2 to 100. Haha, intimidating. Well, how do we do this? The first thing we should probably do is sketch an xy axis as before. We're going from 2 to 100, so we might as well go here, and then I imagine there's going to be a bit of a break in our graph, so we have 1, 2, let's do a few more, 3. I'm going to go past 4 because there's an issue at 4 here, so we'll go 5, 6, and then I'm going to just kind of do a dot, 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 and go way out to 100. Some people might put that little broken thing in there, looks like a heartbeat just to show it breaks. I'm just being lazy and putting some dots. And let's graph the function. One of them is very easy. This is the point 4 comma negative 1. 4 comma, let's put negative 1 down here. So negative 1, 1, 2, a little bit of symmetry. Awesome. Well, we did the easy part. How do we sketch the rest of this graph? We've seen this a few times. I'm going to suggest the same thing as before. I'm going to suggest that you make a quick input-output table, where let's just do kind of what's surrounding 4 here. So let's do maybe 2 and 3. 4 we already know, that was 4, negative 1. And then we also have 5 and 6. And I think we can do some mental math here, especially with these guys. If you substitute 5 in the numerator, 5 minus 4 is 1. Substitute 5 in the denominator, 5 minus 4 is 1. 1 divided by 1 is 1. So we get the point 5 comma 1. If we try 6, 2 in the numerator, 2 in the denominator, 2 divided by 2 is 1. And in fact, all the way down to 100, right? We can do that mental math. 100 minus 4 is 96. Divided by 96, it is still 1. So we can connect these over here, and even we can get really, really close to 4, because if you were to use 4.5, well, that's 0.5 over 0.5, that's also 1. I think until we get to 4, the answer is always 1. The output is always 1. We can't use 4 because it says x can't be 4. All right, what about negatives? Well, if we were to try 3, and I will actually show the work for this one, it's going to become the absolute value of 3 minus 4 divided by 3 minus 4, absolute value of negative 1 divided by negative 1. The numerator, I think, will always be positive. And in fact, I think the numerator will always be the positive version of the denominator. So they are the same number, but with a negative. And whenever you divide something by the same number, it's 1, but then putting a negative, I think, will make these always become negative 1. So negative 1, negative 1, negative 1, and those go out forever, but I'm only interested in going to 2. All right, how do we actually calculate this area? Well, zooming in here, I think we have this first area from here. Then this area is kind of weird. Look at that hole up there, very strange. And then we have a second area, also that hole that goes over here. Well, if you think about the weirdness first and we say, well, I want to know exactly what the area is right here. What is that area? If there's a hole, does this go up forever? Does it stop right there? And the answer is it doesn't matter, because at one specific point, this is just a line. And we discussed earlier that the area of a line is always 0. So if there's just one specific point missing, then all that is throwing off is an area of 0, which is really weird to think that you could have an open circle here and here and here and here, and that is the same area as not having those open circles. Very, very interesting discussion. However, I think we can find this area. Nothing too bad, right? This is 2 times 1, it's a rectangle, and then we could find this area over here. Right? This area is a height of 1, but then what's the base? Well, from 4 to 100 is a base of 96, isn't it? So if we went through and found the area, 2 times 1 is negative below the x-axis. And then above the x-axis, we have 1 times 96. So I think really our area then becomes 96 minus 2, which is 94. Nice. Now, we mentioned 2 ways that you can have a function that's integrable, which means continuity. If you're continuous all the way through, that makes a lot of sense. But the weird one was that there can be removable discontinuities. However, we have other types of discontinuities. We have infinite discontinuities. Normally, those are vertical asymptotes. And we also have jump discontinuities, which we saw here. This is probably better a jump than a hole, but either way, the example held. It turns out, though, that it's much harder to define what happens on either jump or especially infinite discontinuities, and I kind of wanted to show you a few examples here, and you can graph them if you'd like. I'll show you what the general graphs look like. For example, if you wanted to measure the area underneath the graph of 1 over x, and you might remember this rational function from Algebra 2 looks something like this. We have an infinite discontinuity here, and I said I wanted to go from 1, so that's the point, 1 comma 1, out infinitely far and tell me what that area is. Well, it turns out, and we'll see this in Calc BC or Calc 2, that area doesn't exist. There's so much area here going infinitely far, and you're like, well, duh, because, I mean, there's always area, and the graph never gets to the x-axis, so of course it will be infinitely far. But then we have the counter graph to that, and 1 divided by x squared, which will take this guy, flip it up, and slightly change this position. So it's going to be something like this. It's going to get to the x-axis a little bit quicker, and it's going to mirror itself over here. And now we're still going from the point 1 comma 1 out to infinity. And it turns out that area, and I said 0 here, but that's not right, awkward. It turns out that area does have an actual area. In fact, that area turns out to be 1. It's an actual whole number. And so you're like, wait, we measured the same type of area here, but based on this little chunk that still goes infinitely far forever, it might be a number or it might not. Yeah, that's a lot of what Calc BC is. And now we move on to our third example, which actually almost all of these had typos, which is awkward. This one, the fourth one, should just say positive infinity. And the third one shouldn't have anything to do with inverse tangent. Awkward. So our third example is going to say if we wanted the area from negative infinity to infinity of 1 over 1 plus x squared dx, I was probably like, oh, that's the derivative of inverse tangent. We knew that. But either way, I don't know why I'm all over the place here. If you look at the graph of this, not a graph you're expected to know, but it's pretty common one. It kind of loops down like this and then flattens out and then flattens out on the other side. Symmetry again. If you're asked for the area, the total area under there, which I'll highlight in red, you might say, well, again, it has a horizontal asymptote. It never reaches the x-axis. Will this one be infinity? And no, it's not. It's very, very strange. In fact, the area for this one is actually pi. The exact area under there is pi. Again, some more Calc BC stuff, but just showing you that it's very weird when we deal with infinity, whether it's a vertical asymptote or a horizontal asymptote, right? Even with this last one, and I can use the same graph again, this says if you go from 0 to 1 of 1 over x, and I'll show you what that looks like, there's a vertical asymptote here, so it looks like there's infinite area until we get to 1. Well, it turns out that one is infinity as well. Okay, so definitely weird things going on here. So the nice part is in Calc AB, you don't have to worry about that. You just need to realize that your functions will either be continuous or they could have a number of removable holes or sometimes an easy jump discontinuity like this, and it still works. So what did we cover today? Well, we defined a definite integral as having really nothing to do with antiderivatives. We'll connect those later on. But we talked about how the definite integral finds the signed area of a graph. And if you have a graph, it's very easy to count. If you don't have a graph, you need to create one. And if they just give you information about a generic graph, then you use our properties to calculate the area. Next class, we are going to get into all of the other types of graphs. For example, like this sine of x, where we got lucky it went from 0 to 2 pi because we didn't know how to calculate the area. The next couple classes are going to be, okay, what if the area doesn't make a nice shape where geometry can bail you out? What if it's a parabola or a sine function? And we're going to start discussing how we can at least approximate those areas. So thank you for tuning in, and I'm excited to have you guys back for day 69, approximating area.